We've seen the transformation properties for our scalar, vector and tensor properties in the real representation, but now let's use an isomorphism formal definition to transfer everything over into the complex representation and see how the objects transform there. The reason why we're doing this is because when we built the kernels, we chose to use the complex Fourier series to represent the kernel, and so in order to gain a similar perspective on both the kernel and the physical fields on which we're doing convolutions, it's much more fruitful, it's much more unified and elegant to be able to look at both the physical fields and the kernel in a complex representation, and it'll all come together quite nicely in a few slides time, and you'll see why this is really advantageous. Now, in order to do this basis change from the real to the complex representation, we'll use this standard form for our basis change for our isomorphism, and it's this unitary u vector, and q alpha, the rotation operator, will just transform under a similarity transform as normal under a standard change of basis. The scalar property won't transform at all because it's a scalar. The u vector will just transform under the usual basis map. And for the tensor, well, since a tensor is represented as a matrix acting on vectors, changing the basis requires that conjugating the matrix happens so that matrix then acts on the new vectors which have been transformed into their new representation. In other words, written in the new basis. Let's firstly look at our rotation matrix in the real representation. Well, under the similarity transformation, we can write out the unitary matrix and write out the full transformation explicitly in our matrix notation as follows. So let's go ahead and multiply it all out. And it simplifies really rather nicely to this block diagonal exponential form. This is really clean because it's fully diagonalized, and it's actually the two-dimensional analog of the Wigner D matrices in the three-dimensional SO3 case, which will carry over really nicely to the discussion on tensor field networks, which follows briefly. And so that is the transformation of our rotation operator from the real representation into the complex representation. Let's take a look at our friend the scalar. And, well, not much happens as we know, but it's still worth writing it down, right? The vector u, well, we know that it just transforms under a simple basis map, so we'll write out u dagger u, and we'll also make use of the transformation of the rotation operator that we just found. So writing it out explicitly, we can use the fact that u dagger is equal to the identity matrix, and so we'll just sort of insert that in there and it has no effect on anything. And then just by redistributing the brackets, we can identify that quantity in that left-hand bracket as the D matrix. And so the simple transformation law for our vector u is as follows. And it's really rather similar to the real representation, but now we're using the much more simple, complex block diagonal exponential representation. And so our lives are a lot easier because the algebra is a lot easier. Finally, the tensor form. It's rather fiddly, of course, but let's go ahead and write it out. So we'll just use our standard definition. And then by, again, inserting a u dagger, which is just the identity matrix, as well as a u conjugate u transpose, which is also the identity matrix, and then just using, again, redistribution of the brackets, we can identify the quantities in each bracket, along with a bit more algebra, as just more D matrices. So it just boils down to this, which is probably the simplest transformation law you'll see for a tensor, at least in this context anyway. So putting that all together, we've derived the transformation properties for our scalar, vector and tensor properties in both the real and the complex representation. Now let's take a look at what these transformation laws actually look like for some explicit algebra for the scalar, vector and tensor cases, and that will really set us up to see how to do convolutions in the complex representation with both the kernel and the physical fields expressed in the same complex representation.